So we've seen a lot today about the history of the LPI. I'm so honored and flattered that Louise asked me to come here and give a talk about 50 years of solar system volcanism, which as we have seen is like the Reader's Digest version. And it's a huge task, and a lot has happened in these 50 years. And to help put this in perspective, I'm going to offer you a little bit of a timeline. We all have heard that in 1968, the LPI was opened, then the Lunar Science Institute was actually populated in October of that year. But something equally important happened in that year. I was born. You're just jealous because you're over 50. So to help put this in perspective, I'm putting little pictures. This is the biggest one of me you'll see, I swear. Little pictures of me in the corner of the slides just to help give a context of the time frame. As we're moving along. And laughter is so encouraged. Okay, so Louise asked me to talk about volcanoes, and I just came last week from my graduate class where I posed this exact same question, what is a volcano? And it generated 30 minutes of intense debate. I think most of us have a similar idea about volcanoes as the Supreme Court Justice had about obscenity, which is, well, I'm not sure what it is, but I recognize it when I see it. And so what I have decided to do is define a volcano quite broadly as a place on the surface of a planetary body where stuff from the inside comes out due to internal processes. That allows me to talk about geysers. So there we go. So I'm going to, so fasten your seatbelts. We're going to try to do this 15 minutes and 50 years in 15 minutes. And the order of the talk is roughly chronologic because that is the order in which my mother emailed my baby pictures to me. Okay. So I like to think of the Apollo era as the lunar field geology era, right? This is many of our paradigms about solar system volcanism and how the planets are supposed to work came from this short period of field exploration on the moon. And when the astronauts first got to the moon and came back, there were enormous surprises. So much was unknown. And there were some comforts in that most of the rocks and the minerals all looked familiar. There were 3 minerals that were first identified on lunar rocks, but later were then discovered in Earth materials as well. So that's really encouraging for future exploration in that, you know, rocks are rocks, minerals are minerals. So if we educate our students properly, they should be able to go to Mars and identify minerals on the surface. So that was comforting, and we use this term basalt to describe the volcanism on the moon. I put it in quotes because I think if we picked it up on the Earth, we wouldn't call it basalt. Yes, it has a low silica content, but it also has a bizarre titanium and iron contents, giving it a really low viscosity and a strange behavior that we don't see on basalts on Earth. And there were some questions that were hoped to be answered but weren't answered. One that I'm really intrigued by is sinuous rills on the moon. What are they? We know they're lava, but there remains a debate about whether they are an instructional feature, in other words, collapsed lava tubes, or are they erosional features, thermally eroded into the surface. This is important because it tells us about the magma production and eruption rates on the moon and how it lost its heat and the rate at which it lost its heat. So as a volcanologist, this one really grabs my attention. Perhaps surprisingly, we learned that the lunar basalts can erupt explosively. On Earth, basaltic explosive eruptions are generally related to volatile-rich basalts, as we heard earlier today. So this is the orange glass in the Apollo 17 images that led us to realize that explosive behavior does not require great deals of water. It still requires volatiles, and we need to open our minds about what those volatiles might be. From the Apollo era, we thought we understood that most of those lunar basalts were old. That's a paradigm that's continuing to shift. And this is what I was doing during the Apollo era, suffering pigtails. Since then, of course, there's been this renewed exploration into the lunar surface and the lunar history, and it's just been thrilling to see now that I have a little bit more intelligence than I did the last time, during that era. And what we've discovered is essentially more and younger, right? So the moon has been a much more active place and remained a much more active place volcanologically than we first recognized at the end of the Apollo era. This is an image of a skylight a collapsed surface into a lava tube on the moon. And we still don't have the answer to this question about sinuous rills. And if you wondered why you have the red and green glasses, there are a few anaglyphs in this slide, in this talk. The red goes on your left eye. Red is on the left. And I'm cheating because I have the cool 3D glasses, so I can only fold mine one way. All right, so this is an image. This is from the Apollo mission. This is near the Apollo 15 landing site, and there's a sinuous rill. This is Hadley Rill. We're still not exactly sure how these things have formed. So throughout this talk, there'll be a few anaglyphs, and I'll try to draw your attention to them when they come up.
Sorry, what's the scale on this?
So this is Hadley Rill, and Hadley Rill is it's about 100 meters across, so that crater, he could probably correct me if I get this wrong, that crater is probably, it's less than a kilometer across for that crater. No, he's shaking his head, tell me.
And keep your glasses, you'll lose them later.
Yes, don't lose them. So.
It's more like a kilometer across.
Kilometer across?
Yeah.
Yeah, oh, the rill, right, yes, thank you, yes, the rill's about, yeah, thank you. So after our experience with the lunar geology, I remember the cover of Time magazine when the Viking landers arrived at Mars. And Scott just gave a wonderful summary of kind of what we learned about Mars and when. And as a volcanologist, of course, I'm interested in the fact that Mars has the tallest volcano in the solar system, Olympus Mons, and Pat McGovern always reminds me that it also has the fattest volcano, which is Albus Mons. And our studies reveal, as Scott said, warm, wet, early Mars, but that has implications for volcanic styles, right? If we have a lot of water, then maybe we can have explosive volcanism on Mars, more common in the past than in the present. And of course, we know a little bit more about Mars composition because of the meteorites. So here's your anaglyph of Olympus Mons. Someone who's smarter than I once did a calculation where if you were standing in the middle of the Olympus Mons caldera, and the entire volcano is about 600 kilometers across, if you were lucky enough to be standing in the middle of that caldera, combined with the size of the caldera and the curvature of the planet, you may not be able to see the edge of the caldera. You may not even be aware that you're in a crater. So this is an enormous volcano. Those calderas, nested calderas, suggest repeated eruptions and collapse of the surface from magma withdrawal and implies that there is a magma chamber shallow within the volcano. A long-lived, large magma system in the presence of water. I'd like to know, to all you petrologists out there, where are my andesites, dacites, and rhyolites that should have been in this volcano? So there's still more that we don't understand. And this is how old I was. 3rd grade when I saw that Viking orbiter lander, or Viking lander on the cover of Time magazine. So the next enormous solar system discovery in terms of volcanism was volcanoes on Io, active volcanoes on Io. This is the first place in the solar system where we saw volcanoes erupting somewhere other than Earth. This was really exciting. And it was the ultimate called shot, where the prediction that Io should be volcanically active occurred a few months before Voyager actually got there. And now Io has been considered by some to be the most volcanically active body in the solar system because at any given time it has around 20 volcanoes erupting. And the sulfur in the lavas are what give it this wonderful color, although the volcanism on Io is still dominated by silicates. And so if we go to Io, we should be able to recognize the rocks and minerals, which is pretty exciting. I also feel compelled to point out that at any given time, Earth has about 55 volcanoes in active eruption, and that's only the ones on land. So I would say Earth still wins. And then we skipped 10 years because Voyager was working its way out to the outer solar system. And I was an intern here in 1988. We were still in the West Mansion at that point. And these are the people that went on to publish papers in planetary science. Ann Theriot was working on impact craters. Nate Bridges, myself, and Sue Sakamoto, who will be my roommate at LPSC, so come in full circle. My advisor, my mentor, was Sean De Silva. When I first received the acceptance letter, I was told I would work with Peter Francis. But when I got here, Peter was awfully busy, and now I know that he was working with Lori. So he didn't have time for me. So instead, I was working mostly with Sean, who was under Peter's supervision. They were working on getting the figures ready for their book on volcanoes of the Central Andes. And so my very first job as an intern was Sean had set up on a huge conference table a map of South America, because for image resolution, image quality in the book, we had to make it bigger than it was going to be in the book. And my job was to take my shoes and socks off and crawl around on the table and map all of the volcanoes. And it took me about a week and a half, and I just did it before I left on Google in 30 seconds, so that's okay. And I would also like to formally thank Pete Schultz, because I asked him to write me a letter of recommendation for this internship program. And now I recognize that what probably happened is he wrote them and said, I have served you with your internship program for all these years, and now this undergraduate wants to spend the summer working with me. Dear God, please take her. Thank you for the opportunity. All right. So when Voyager 2 flew by, I was at Brown University working in the RPIF there with Pete and Jim Head, and so it was really exciting to be there and see all this data as it was coming down. And I learned a brand new word, which was cryovolcanism. This is a mishmash of terms that was really coined to describe some of these volcanic activities that we're seeing in the outer solar system, where it's not silicates, so it would be liquid or gas on Earth. So methane geysers on Triton, and possibly some cryo flows on Triton. And I couldn't find a picture of myself from '89, but this is a picture of Barb and Pete at the fall picnic in 1989. And how he maintains his girlish figure. Okay, so here we now in 1990 we got Magellan, and here's another anaglyph. As you know, things on Venus, everything's got a naming convention, and on Venus, everything has to be named after women or goddesses, with one exception, which is the tallest, most radar bright feature on the entire planet, called Maxwell Montes. That's okay, it's smacked on the top by a crater called Cleopatra crater, and there still remains some debate over whether Cleopatra is an impact crater or a volcanic crater. Probably both, possibly certainly an impact that may have generated some volcanism. No one really expected Venus. Boy, were we surprised. There were some strange volcanic features on Venus that we haven't seen anywhere else. These fun pancake domes, these weird folded things, but most of Venus volcanism was shield volcanism, basaltic volcanism, and we felt pretty comfortable. My favorite features on Venus are these long channels. It turns out that the longest channels in the entire solar system are on Venus, which has no water, so that's kind of funny. And so people have called into the concept of exotic lavas, carbonatites, komatiites, sulfur flows, to try to explain some of these long channels. So I spent the early part of my graduate career working on these flows. I graduated from Brown in 1990 and got married in 91, all while trying to understand what Magellan was trying to show us. The next big influx of data came from the Galileo mission, where we learned a lot more about Io. Loki Patera here is probably one of the most energetic volcanoes in the solar system. And we also learned more about Europa, another cryovolcanic place. And there are still so many outstanding questions about Europa. So I'm glad to hear that people are seriously talking about going back. So here's another anaglyph. This is a part of Connemara chaos, and another chaos terrain. Here's your scale bar, 15 kilometers. A really crazy place that makes you think twice as a volcanologist, because every time you learn about how the physics of any silicate material works, you know, it freezes and then it gets more dense and it changes this, and every time you learn something like that, the next line is, except water. Water doesn't behave that way. Water is strange. And here we have a whole planet where water is strange. Oh, and there were more Gregs forming, along with cryolavas. I had my son in 1998 when these data were coming back. And around the same time, we had the extra fleet of missions to Mars, and this is my favorite data set for all of Mars, and I still feel if I could choose only one data set, it's going to be detailed topography, because we can get so much. We thought we had a good handle on what Mars was trying to tell us, and now with these data, we realize, oh my gosh, there's so much more. There are more volcanoes than we ever thought. Younger volcanoes, pyroclastic deposits, but there are still outstanding questions. Huge tracts of Mars covered by this deposit known as the Medusa Fossae Formation. That's my timer. And, of course, another Greg in 2000. And Cassini, oh my gosh, I don't think anyone expected this. I love it when we're surprised in science because that means we have so much to learn. The tiger strikes and geysers and Enceladus. Here's another 3D image of those tiger strikes. So this, okay, this one here is Baghdad Solstice right here, where material comes out from the interior of Enceladus, covering the surface. So an amazing body that no one predicted to be as active, I think, as it is. And of course, Europa and Enceladus both have powerful implications for habitability, as we've learned. And when these data were coming back, I was busy teaching my children how to read. Messenger, we heard a lot about Mercury, and boy, were we surprised. I think this is my overarching take-home from this talk is, boy, were we surprised, and isn't that wonderful? Because that means we have so much more to learn. For me, the biggest surprise on Mercury were all of these pyroclastic deposits. So here's a planet that has no plate tectonics, is supposed, no water, and yet we have evidence for explosive activity. And a huge lifetime of volcanic activity. Or my kids got a cat when Messenger flew by Mercury. We didn't plan it that way. We did have a cat named Amalthea, though. And of course, Pluto, which I was reviewing some of the early papers on Pluto, and then as part of that, some of the early press releases. And it's just wonderful because, again, oh boy, were we surprised. Nobody really predicted this for Pluto or Charon. This has been proposed as a putative cryovolcano, this time out of nitrogen. So a lot more to learn about the behavior of the insides of planets coming out. So 50 years, we've had lots of surprises, and that is a good thing. Scientific surprises are wonderful because it forces us to rethink how we believe the universe works, and that's always a good thing. The more data we have, the more surprises. The best part about these planetary exploration missions is we're always getting more data, which raises more questions, which drives more data, so it's wonderful. So here's to another 50 years of the LPI and more shades of gray, and my family thanks you.